So taking off from where we left off in part 1 of limits, let's look at a few examples where we apply the different rules or operations related to limits. So in this example, we're asked to find the limiting value of this expression x squared plus 5x as x tends to -2. Now, a straightforward way to solve this would just be to plug in the values of x is equal to -2 into this expression and calculate the answer. And later on, I'll tell you why that would be feasible, because x squared plus 5x is a polynomial function, and by default, polynomial functions are all continuous. But let me not, I think I'm way ahead when I speak that. Now let's just evaluate the limit of this expression. So how do we do this? Now this is a sum of two functions. So let me rewrite this as limit of x squared plus limit of 5x. And now within each of these, x squared is a product of x times x. So let me rewrite this particular first term as limit of x into limit of x. And in the second case, if you see, it's going to be limit of 5 times limit of x. Now limit of 5 is just going to be 5, so I put that right here. And then I then write limit of x as x tends to -2. Now it is of this form which we saw in the previous video. And now I'm just going to plug in the value of x is equal to -2 into this expression. And I evaluate the limit and I calculate that to be -6. Let's try another example where we have to find the limit of this particular function as x goes to 2. Remember, this function is no longer defined when x is equal to 2. But we can still go ahead and see what's happening in the vicinity of x is equal to 2. And if I straight away plug in x is equal to 2, we're not going to get anywhere. So how do we solve problems like this? We factorize. Now, if I rewrite the numerator in this particular manner, x squared plus x minus 6 can be factorized into x minus 2 times x plus 3. Now, for all values of x not equal to 2, I can go ahead and cancel these two terms. And I'm able to do that because I'm not looking at the functional value at x is equal to 2, but rather what's happening around x is equal to 2. So x is not essentially equal to 2 there. So I can go ahead and cancel these two terms. And I'm left with a much simpler expression of 3 times x plus 3. And now in this particular case, I can go ahead and plug in the values of x into the function and calculate the limits. Let's see another example. This was something that we saw earlier in the last video. Let's see another way of evaluating these limits. Now, we want to find the answer when h tends to 0. Now, if I plug in h is equal to 0, we're going to have an undefined expression and we can't go anywhere from there. So how do we get around this? One way is to multiply and divide by square root of h plus 1 plus 1. And the reason we do that is that the numerator is now of the form a minus b into a plus b. So I can rewrite that as a square minus b square, which is what I do here. And I end up with an expression that looks like this. Now, in this particular case, because I'm interested in what's happening in x at values of h very close to 0 but not equal to 0, I can now go ahead and cancel h. And I am now left with an expression of this sort, and I can go ahead and plug in the values of h is equal to 0 here and calculate the value of the limit. If you recall, we ended up with 0.5 or half when we did it using when we did it using a table of numerical values. So this is just another way of evaluating the limit. And I've left another question here as an exercise for you to solve. So plug in the values and come up with the limiting value of this function. Another useful thing to do here might be to try out an online graphing calculator tool and see if you can plot all of these functions and visually try and understand what's happening when you're trying to find the limiting value of a function at a particular input value. So this is a great exercise to build your intuition about graphs and also get to review your concepts on limits. So please do that. Now, it's important to note here that when I talk about the existence of the limit, I'm referring to the limit being a single real valued number. So should I say single real number value? Anyway, you get the point. So the limit needs to be a real number, and for a limit to exist, when you approach the limiting, when you approach the function, when you approach the x value from both sides, the function has to approach a single value, and that single value has to be a real number. And only in that case, we speak about the existence of a limit. Now, and that's what we've been doing so far. We've been looking at examples of that sort. And sometimes just saying that a limit does not exist in a particular case doesn't tell us much about the function. Now, there could be cases where the limit doesn't exist, where, when you approach the value from the left or from the right, maybe the two numbers aren't referring to the same number, but nevertheless, one-sided limits can still exist when a function doesn't have any limits. Let's see an example here. Now, if we are given the function g of x is equal to mod of x minus 2 by x minus 2, now let's see how the graph of this function looks. So for all values of x less than 2, it's going to be minus 1. And for all values of x greater than 2, the function is going to have the value plus 1. And the function is undefined at x is equal to 2. Now, what's the limit, or what's the value that the function is tending to as we get close to 2 from the left-hand side? If we get close to 2 from the left-hand side, the functional value is minus 1. On the other hand, if we get close to 2 from the right-hand side, the functional value is approaching plus 1. So because these two functional values are different, we say that the limit does not exist at x is equal to 2. But on the other hand, the one-sided limit exists. In other words, if I approach x from the right-hand side and I write it in this manner, the limit of this particular, the limit from the right is given by plus 1. And the limit, when you approach it from the left, which I write in this manner, this is given by minus 1. So oftentimes one-sided limits can still exist, and that is still useful for us to kind of understand. So in this particular example, when I give you g of x and I tell you these, when I give you these results, it's easier for you to visualize how the function is now going to look at or around the point x is equal to 2. So that's where one-sided limits come in. Let's see another example here. Now, we are given this piecewise function, where for values of x less than 2, f of x takes on f of x is given by x plus 1. And for values of x greater than or equal to 2, f of x is given by x squared minus 4. Now, what's the limit of f of x as we approach 2 from the left-hand side? Which is, when we approach 2 from this side, f of x is now tending to 3. So the left-hand limit here is given by limit of f of x as x tends to 2 minus is given by 3. Now, what happens to the limit when we approach x is equal to 2 from the right-hand side? Well, when we approach 2, we're going to be looking at this part of the function, and that functional value is approaching 0. So the limit of f of x as x tends to 2 from the right-hand side is given by 0. And in this example, where we had a h of x function, which we saw earlier on in the first video, let's try and find the limit of h of x as we approach 2 from the left-hand side. So we're approaching 2 from the left-hand side. And as we approach 2 from that direction, h of x is tending towards plus infinity. And when you approach 2 from the right, well, there again, h of x is tending to plus infinity. Now, and we see that it so happens that as the limit, both the left and right hand limits are the same. And we say that as we get closer to 2, h of x is going to get closer to infinity. But though we're talking about an infinite limit here, remember that we say that a limit exists only when the limit can be denoted by a single real number, a real valued number. Here, the limit, we're talking about a limit being infinity, and that technically doesn't count as a limit. We're still trying to understand the behavior of the function here. So when we say infinity, it helps us visualize the function better. But that still doesn't mean a limit exists. So the limit technically exists only when f of x approaches a real number L as you get closer and closer to A. Now, just a quick another example here. So when you have the function say 1 by x and you're interested in understanding the behavior of 1 by x as x gets closer to 0, when x approaches 0 from the left-hand side, the function is going to approach minus infinity. And when x approaches 0 from the right-hand side, the function is going to approach plus infinity. And now the left-hand side limit and the right-hand side limit are not the same, and they also happen to be infinity. And so the overall limit, the two-sided limit for this function does not exist. And I'm going to leave it as an exercise for you. Oh, wait, I've already cracked this. So y is equal to 1 by x. For positive values of x, looks like that. And for negative values of x, it looks like that. So that's just another example for you to understand the concept of two-sided as well as one-sided limits. So in the next video, let's go over continuity of functions, and I will see you there.